Well, looks like it's time to start, folks. I think it's just going to be us today, but again, we'll still run the Zoom just in case folks come in. But any questions you'd like to start out with today to get us started? Definitely kind of up to you two folks, since you're kind of the only students here at the moment. Okay, well, we left off on section 4.3. We didn't get too far. We just pretty much introduced it. Our goal today is really just to finish off this section. And if we have a lot of additional time, we'll take a look at 4.4, but I mostly post it just so it's available. That way we can know what's coming next. So in section 4.3, the major thing we're looking at is we're getting back to the definition of linear independence, linear dependence. And this definition was tricky in a certain sense. We've never really used it directly. Pretty much what we did with this definition is we just took vectors, say vectors like these, threw them into a matrix and counted pivots. So we never had to use that definition directly. But suddenly out of nowhere, for this problem, we did have to use it directly. We had to take specifically for these two polynomials, P1 of t, P2 of t, write out this linear combination. So that was our x1 and x2 multiplying the two different polynomials. And then we have to determine if the only solution is trivial or if there's a non-trivial solution. That's a lot of work, actually. And this is a simple case, just two polynomials with two terms. You could imagine how this could get really nasty, like 5 polynomials, all cubic. It'd be just lots and lots of algebra. But what it all boiled down to is this information. We equated coefficients, and now we have a system of equations on those coefficients. So somehow, some way, it all came back to linear algebra. And we found out that, well, once we reduced to reduced row echelon form, the only solution to this vector equation above is x1 and x2 had to be 0. So that gave us linear independence on the original set right here. That's kind of our really fresh warm up on this problem. Any questions at all on getting through this one? Okay, again, like I mentioned, this is a pretty tedious process. So what we want to do is not necessarily work in P2. What we're trying to get to is a way to find the dimension of P2 so we can correlate it with something like, say, R3. Turns out they're isomorphic. But to do any of that, we have to go back to this right here, the basis for a vector space. Good news is we're just about there. A basis only requires two things. It's a spanning set that has to be linearly independent all at the same time. Now, once you have a basis, we come down here and we just say the dimension of a vector space is equal to the number of vectors in the basis. So it seems kind of strange in a way. This feels like a mysterious definition we've been hinting at all along, but all it really is issues with spanning and independence. You find a basis, count the vectors, and you've got a dimension. Well, we'll define dimension very formally in the very next section. For the moment, we need to practice just dealing with bases, which is, by the way, plural for basis. So if you ever hear me say bases, we're not talking baseball, we're just saying plural for basis. Well, any questions so far, folks? Okay, well, let's take a look at the whole definition. First, I put down this definition here just as kind of an additional information. This is really a recopy of the information we had from chapter 1. It was a reminder that if you have a set of vectors, well, if your set contains just a single vector v, linear independence means v is not the 0 vector. If we have two vectors, we'll say that that's linear dependence if and only if they're not multiples of each other. And finally, any set of vectors containing that 0 vector is also automatically dependent. So we'll be using those ideas in these notes as we go through. They're still really good at concepts. I guess it's all carryover from chapter 1. But now here's one of the major definitions in linear algebra. Really one of the major objectives of the course is to get to right here so that we can define dimension and start working with eigenvalues, eigenvectors. And so here's how our author tunes it. He talks about the subspace, but keep in mind, a subspace is a vector space in its own right. At the same time, if we're talking about an ordinary vector space, it can be thought of as being a subspace of itself, just a trivial kind of subspace. So when we have a subspace, we find an index set of vectors. It says it's a set of vectors in V, and that makes sense because if H is a subspace, it's also a subset of V. Everything in H is also in V at the same time. This little symbol right here is sometimes referred to as a script V. People like to write a fancier set with cursive if you like, but you don't have to do that. I'm not great at duplicating that. I'll try to usually write it this way. But it's just a way to alert the reader that this set is extra important if you suddenly see cursive or other special symbols like that. So it's an index set of vectors. Indexing just means it's ordered. You have a B1, B2, all the way through BP. There'll be a basis for H if we have that set is linearly independent and that it spans the set that we're interested in. So again, that's the whole definition right there. Any questions at all, folks, with their finally basis definition? Okay, example 2 is nothing too major. Really, the major thing we're going to look at to practice this definition is down here, looking at various sets, just deciding if they're bases or not. But this is a good one to get started because this set has a name. It's called the standard ordered basis, and sometimes it's also called the canonical basis. Anything that's called canonical, or say like the canonical basis, just means it's a natural choice for a basis that just sort of pops out right at you the moment you're trying to look at a basis in R3. This would probably be the first one you're thinking. To show it's a basis, well, we just have to check two things, independence and spanning. Or you could also use the vertical matrix theorem and really tie this out really quickly. But to practice with this definition, let's start by just doing this. Let A be equal to E1, E2, E3. Well, the next thing we have to do is just recall what these things are referred to as. Anyone recall what E1 ought to be? Exactly, we'd go 1, and then just zeros down below. So it's the first column of the identity matrix. Go to E2, and that's the second column, 0, 1, 0, and then finally 0, 0, 1. In other words, in the canonical basis, all we've done is we grabbed the 3 column vectors from the identity matrix and collected them in a set. But the moment you do that, notice that that's a nice matrix. It's a square matrix, it's invertible, it has determinant 1, it has all sorts of great features. But just for the sake of review, let's go through this one at a time, even though you could just say the determinant is not 0, so it's automatically a basis at this point. Let's also just say, for the sake of review, since there is a pivot in every column, the columns of A are linearly independent. So that takes care of that first portion for independence. But because it's a square matrix, if there's a pivot in every column, there has to also be a pivot in every row. So we can also say there is a pivot in every row. And so you could say this a couple ways. The columns of A, which is all of this, spans R3. Or you could just put span in front of this and say span of those 3 vectors is equal to R3. Let's go with that route. Span E1, E2, E3 must be the entire space, R3. Then our work is done. We can just conclude by saying this shows E1, E2, E3 forms a basis for R3. And that's our pretty much the whole set of work for this one. Any questions at all, folks, on running through that definition? Okay, so that's our really important basis if we're dealing with R3. If it was R2, it'd just be E1, E2, and we take out the last entry here, making it 2 entries. So that's a great basis, but we're going to find in chapter 5, it's not always the basis you want. Sometimes when you're doing problems, you do want to make a change of basis, and that's part of the interesting things that we're going to do with eigenvalues and eigenvectors. Sometimes we'll go for a strange looking basis only because it's suited to the problem at hand. Usually we're taking a look at applications for those settings. So after doing all that, this definition right here is just reduplicated, and down below is just practice working with bases some more. So we're going to make some interesting observations as we do this. It says, which of the following sets form a basis for R3? We'll justify our answers. In an exam setting, I'd probably take this off because the exam would be too long otherwise. But here we'll justify it because it's our chance to practice these ideas. So we have two vectors here. They look like they have some nice features. But would you say this forms a basis? Yes, absolutely. In order to get that spanning, we would have to have three pivots altogether when it's thrown to a matrix. So good call. This one is absolutely not a basis. So the justification depends on how much writing you want to do. You could make this kind of fast. You could say let A be 1, 0, 0, 0, 1, 0. Then you could also say the columns of A do not span R3 because there's not a pivot in every row, like you said. But you can make that statement in even faster. You could say then call A is not equal to R3 since there is not a pivot in every row, or we could have just said there's not three pivots. We require three pivots altogether. The reason we can just say that to make it real brief is because call A or column space A is just the span of the columns of A. So it becomes just a really, really fast shorthand if you decide to use that. Although you don't have to, it's throwing more symbols into the mix. But we still have to give a conclusion. We need to say here, not a basis. Well, that's one down. Let's take this definition with us as we go. And the reason that this one wasn't a basis is the same reason for this one. Would you all agree? There's just not enough pivots. So we can duplicate our answer and say, if we want to make it even more brief, you can start introducing more symbols. V1, V2, V3. Let me fix that 3 though. This is kind of lazy notation, but our author himself uses this to define V1 as this vector. You usually want equality there, but the meaning of what is being said here by the author is pretty clear. V1 is going to be that vector, V2 is that vector, and so on. So I'll just copy our author's use of notation there. Then we can say, let A be equal to V1, V2, V3. And again, there's lots of things we can do. But if we're thinking about spanning or linear independence, then, well, we could do the following. Let's take the determinant of A. It's automatically 0 just right out of the gate because you could do a cofactor expansion. This is not a matrix, but imagine it as a matrix. You just do a cofactor expansion down the third row. But if the determinant of A is 0, then this implies A inverse does not exist. Oh, and let me cancel that out. Now, if we're thinking about the invertible matrix theorem, then that's pretty special. If A inverse doesn't exist, then back down here on the invertible matrix theorem, tells us lots and lots of stuff, but in particular, it says the columns do not form a linearly independent set, and it says the columns do not span Rn. But just one of these failing means it's not a basis already, and both fail for this problem. So coming back up, we can say by the invertible matrix theorem, let's just go with, say, independence. The columns of A, oh geez, don't know why that keeps popping up. The columns of A are not linearly independent. So our work is done on this one, but again, don't forget the conclusion. We have to say not a basis. So that's two down, both of them not bases this time. I think most of these aren't bases, but it's not always clear why that's the case. Except if you look at this one, what would you all say is obviously wrong about that set? Exactly. The moment that's tossed in there, the whole thing is linearly dependent. So pretty much we just have to say, don't know why I'm changing colors, but just to make it interesting from one problem to the next, let's say here, the set is linearly dependent due to the zero vector. And just to emphasize, there it is, that's our zero vector. We're usually seeing it with that symbol a lot often. And so we're done. If we lose linear dependence, again, we don't have a basis. So this is not a basis. So 3 non-bases, pretty much all this really is just another look at what we did in chapter 1 of independence and spanning now all at the same time. So here's our next try. How do folks feel about this set? This would span when you look at it, right? It looks like there's certainly a pivot in every row, but would it be a basis? Exactly. I think the theorem that most people would think about when they see this is a statement that goes along these lines. There are more vectors, 4 of them, than entries per vector, 3 of them. And then like you were saying, whenever that happens, if you set this as a matrix equation equal to 0, there's a free variable just guaranteed now. And if there's a free variable, we lose linear independence. There's going to be non-trivial solutions immediately to that kind of system. So we can conclude here, this implies the set is linearly dependent. And so it's not a basis. So that's several of them so far. Does that make sense to folks with the issues at the moment? Awesome. That's the problem with the basis, is that it is restrictive when we have to hit those 2 different conditions. Then coming down next, I feel like this one is the trickiest one of the whole set, because looking at this, it is a basis. But if we scroll up, the question was, is it a basis for R3? So now that's a technicality, right? It makes it an awful trick question, but it is something that we have to watch out for. The trouble here is, well, this is not even a set contained within R3. And so the question is just not well defined for this. Let's say not a basis, since the set is in R2, not R3. So watch out for that one. That's a horrible way to lose a point, but it is still an important concept to always watch out for the major vector space we're trying to work in. But just to clarify, this is a basis for R2, because we took the canonical basis, that's column 1 of the identity matrix, and that's column 2 of the identity matrix. Or it's also called the standard order basis. Well, last one in the set that's been not a basis like 5 or 6 different times. But looking at this one, what would you all say about this? Would it look like a basis by just visual inspection? Yeah, I would agree with you. Lots of things you can say here. You can take a determinant, or yeah, let's go for a determinant. Let's call this B1, B2, B3. Let A be equal to B1, B2, B3. And just for the sake of the notes, let's also expand that out. You could skip this next step. It's -3, 0, 0. 510, root 3, 5, -5. Then finally down below, we can say the determinant of A. Exactly, we just multiply through the main diagonal. That's why if you left it right here, I'd say it's okay because you're probably looking here too, right? You're getting 15 either way you consider it, which is not 0, which then implies A inverse exists by the invertible matrix theorem. Now, if we look at the invertible matrix theorem again, I mean, we know what's in there. There's spanning and linear independence all wrapped in one. But now it's been updated in this chapter. There's also just this statement right here. The moment you know your matrix is invertible, its columns will form a basis just immediately. That's kind of nice. If you can just see the pivots, that'd have been just a fine way to go as well. You might have just said, it's an echelon form. There are 3 pivots. By the invertible matrix theorem, this set forms a basis. So let's say it here. The set forms a basis for R3, again, using the invertible matrix theorem. So that's what bases look like. This one was a basis, but for the wrong space. And anything that's not a basis, well, notice what happens. Either you had too many vectors that forced it to be linearly dependent, or you had too few vectors that just lost spanning, or the vectors were the right amount, but they happen to be dependent. But one idea here that we ought to take a look at is, we're talking about a space for R3. This is a bit of a preview, but it does help out already. Every basis has 3 vectors. Why is that? Well, we have to do some work on dimension, but we know the dimension of R3 ought to be 3 for a well-defined dimension that follows the intuition we're going for. And so anything that had not 3 vectors was automatically excluded, even if the set spans, for example. The only ones that were a candidate for a basis had exactly 3 vectors, but then a lot of these lost something, spanning on this one, independence was lost on this one. This one is automatically excluded, and so is this one. Even though it's a basis, we're going for R3, so 2 vectors is the major thing to look for. There has to be exactly 3 vectors for a possibility, and this is the only one that actually did the job for us. Well, any questions at all, folks, with independence at the moment? Okay, so that's our rundown, and you might feel like pretty much what we did was, this is just a review of chapter 1 in a major way. We're reviewing independence and spanning for these kind of problems. Now, with all these tools available for us, I put this example 4 here mainly as just a reminder that we have the invertible matrix theorem right here. So example 4 wasn't meant to be anything major. In fact, we've argued the way we're about to in example 4 already. And so it says, if A is an n by n invertible matrix, explain why the columns of A form a basis for Rn. Let's just briefly write, since A inverse exists, the invertible matrix theorem shows the columns, let me try to spell that right first, columns spans Rn and are linearly independent. So that's all we had to have is the linear independence, the spanning, and that's a really fast justification right here. Well, any questions at all, folks, with the new invertible matrix theorem or our new definitions? Okay, other things that are new here as well is, if you have an invertible matrix, it would tell us that this system right here has only the trivial solution, and that means if we go to look at the null space, when there's only the trivial solution, the null space is exactly just the 0 vector, which would also mean, down below, the dimension of the null space has to be 0 in that case. That's an interesting definition, but this is the one time where a dimension comes out as 0, if you have the trivial subspace right here. So that's our brand new theorem. It's almost a guarantee this one is going to be on, I should say almost, it is a guarantee this one will be part of the last page of notes for the third exam. So it's a good theorem to get acquainted with. And we will have, I believe, 1 or 2 more additions in chapter 5 about eigenvalues coming up next. But aside from that, here's one of the majorly important theorems in this section, the spanning set theorem. It tells us a lot of stuff, and it first says, take a set S of vectors in a vector space V and form a subspace by just spanning those vectors. By theorem 1 of this section, we know that this is automatically subspace the moment you put span right in front. Now, that's great. You can get a subspace really fast by spanning. Say, for example, here's one. It's a subspace where we span a whole bunch of random looking vectors, but we often want to find a basis. And so, well, we need to pare this down. Just take the vectors that actually matter. That's what the spanning set theorem does for us. It says, if one of those vectors, say vk, maybe that's the second one or the third one or so on, if it is a linear combination of all the others, then you can just delete it from this set, and that set can still span H. It's kind of amazing in a way. So all you want to do is find which ones truly matter. We can take this part A right here, and this is essentially a corollary. Oftentimes, we're trying to find independence or dependence. You notice we put things into a matrix very, very often. And you're trying to find a basis for this set right here. What you would do is throw the vectors inside of a actual matrix A, find the pivot columns, and anything that's not a pivot column, you just delete. Take the original pivot columns from the matrix A, and that's your basis. So we'll practice that in examples 5 and 6 just to see how this all goes. But one thing that's really tricky about theorem 6, easy to miss, I've made this mistake myself quite a lot. When it says the pivot columns of a matrix A, we really mean of the matrix A right here. Let's emphasize that. What we mean specifically is not the row reduced matrix. So we have to go back to the original matrix A, find out what the pivot columns are, and pull only these columns. It's tempting to have the columns from the row reduced matrix because that's where you'd be looking after you finish the problem, but those can and sometimes are, and specifically in this problem, the wrong columns to grab. Well, any questions, folks, with the work we're about to try on example 5? Okay. Well, other thing that goes on in the spanning set theorem, our author sometimes combines loads of statements into one. We'll see more of that in chapter 5. But this is an interesting side fact. If H is not the trivial subspace, and if H is truly a subspace of V, there will always be a basis. So we can always find something inside here to pare down to and drill down to the real basis for that set. That's what we'll do right here. It says find a basis for the column space and the null space of A. So this looks like a heavier computation kind of problem. If it just said column space, all we need is row reduced echelon form. Or excuse me, if it just said column space, all we need is echelon form, so we can save a lot of time. If we're looking for the null space, we're actually solving a x equals the 0 vector. So we need row reduced echelon form for this whole problem. We'll start by just taking A and begin by row reducing it very carefully. That's a 4 by 4 one. Always seems to be some kind of row reduction in these chapters. So first, let's copy 1, 2, negative 1, 1. Let me know if my arithmetic here goes sideways. Really easy to do right before we begin. I'll multiply by negative 2, add to the row below to get 0, 0, negative 1, negative 2. Now next, multiply row 1 by negative, oh, not that, row 1 by negative 1, add to row 2, and we should get, let's see here, 0, 0, 2, and a 6. Or no, that should be a 4, right? Forgot it's a -1. There we go. Finally, just take row 1, add it directly to row 2, and we get 0, 0, 0, 8. So this one looks like it should resolve pretty quickly. Let's continue on. Because we've done lots of row reduction, shortcuts are almost encouraged at this point. In the homework, if you've got to this stage, I would encourage you just to go like this next. That way you're not pairing over an entire 4x4 matrix. As a shortcut, does that look all right to folks? Okay, we'll continue with that. If you see something odd like a plus sign, you can just assume we switched the sign to save a step. So let's now copy in rows 1 and 2. Now we'll take -2, multiply row 2 to add to row 3. This will give us 0, 0, 0, 0. Now down below, we can just divide this row by 8. That'll give us 0, 0, 0, 1. Almost there. What we need to do is switch these two rows out, but also, if you have a pivot here and zeros to the left, these are automatically just gone. You can imagine the row operation is -2 times row 4, add to row 2, that's gone. But these are completely unaffected. So if you want to take even more shortcuts here, some people might do this, not that. Just throw in a 1, 0, 0, and you're pretty much done. That's going to look really weird on the note, so I'll take one additional step and write this in as, let's make this our last row. And I did forget to do one thing. I should have eliminated that entry right there. Forgot we're going for reduced row echelon form on this thing. That's okay, we can take an extra step to complete this. So now this is going to be row 3, 0, 0, 0, 1. Then we have 0, 0, 1, and ordinarily a 2, but that one's going to get wiped out, so I'll put in a 0. And finally 1, 2, -1. And the one that would have gone here also dies off. So here's our next result. Again, I missed this part right here. We need to eliminate that entry. But maybe before we get too far, let's go for this right here. We're already in a good position for the column space. To get a column space, we have a pivot here, here, and here, and they correspond to columns 1, 3, and 4. So we might as well answer the question right here, basis for the column space. Now the way we write this is very particular. We know that the column space of A looks like this, span of V1, V2, V3, V4. So in other words, the column space is the span of those columns. But if you're asking for a basis, we actually can't say span right here. And the reason for that is, suppose you span this vector, 1, 1. Now, the vector 1, 1 is linearly independent. It's not the 0 vector, it's a set of just one vector. So that's a linearly independent set. But this is linearly dependent. And that deserves an exclamation mark because it's not completely clear all the time why it's dependent. Do you see why it could be considered a dependent set just by visualizing it? It's tough. And one thing that makes it tough is set theory doesn't necessarily help. If you wrote it out, it's C, 1, 1. I guess set theory helps a little bit, such that C is an R. Still, it's dependent, but this points a little bit closer to what the actual issue is. So once we write that, C is a parameter, it can take on any value. And so if we were to write out the elements of this set, it's impossible. I cannot list out infinitely many different vectors indexed by real numbers, but I can start throwing in some things that are there. There's a 1, 1. There is a 2, 2. There is a 3, 3. And I have to do this Well, doing it forever is not enough. There is uncountably different many vectors in here. So I'll just go dot, dot, dot. But that's a linearly dependent set automatically. There's way too many vectors inside there. 2 vectors at most had the chance of independence, so 3 causes dependence. So all of this to say, if you're going to find a basis, you can't express your answer using span. We have to give just the set. It's a weird technicality. You wouldn't lose a lot of points, but it's a good concept to keep in mind. Span is always a tricky concept to work with. Does that make sense to folks so far with those issues? Okay, so because we're writing a basis, we avoid linear dependence, and we just say basis of the column space of the matrix A is, we just throw in those 3 vectors, 1, 2, 1, -1. -1, -3, 1, 1, and 1, 0, 5, 7. So we're halfway done. We've got the basis of the column space. Any questions at all so far?
Question about the span of 1 and 1. So I mean, can we see the span as an individual, or it's always a group?
It would have to be thought of as a group, yeah. The only way we can think of it as just one single element is if it looked like this. The span of the 0 vector is the one and only exception where that just turns into the 0 vector and nothing else. Only because when you multiply here, you're just getting the 0 vector back every time when you try to rescale. But does that answer your question about the single element?
So in this case, that so for example, with the 2, 2 and 3, 3 is this span of 1 and 1. Is it because it's multiple of the?
Exactly, yeah. The multiple is happening right here. And when we got to this one, that's when C took on a value of 2, and so on, absolutely. So kind of the visualization of this as a spanning set is it would have looked like this. We go to 1, 1, so there's that 1 vector. But then everything I was plotting is just discrete points on that set right there. Contains the 0 vector and everything else as well. Awesome. Other questions about this so far? Okay, so getting the basis for the column space, not too bad. All you do is get echelon form, grab the columns from right here. Let's mention that again, because this is an easy mistake to make. And sometimes if you made this mistake, you might still have the right answer, but this time that's not the case. If you grab this column, this column, and this column, one feature of all those is that the 4th entry is always 0. But if you take these things, there's a way to get a non-zero 4th entry when you span those 3 different columns. Whereas over here, that's impossible. So spanning these does in fact give you a different spanning set than when you span the actual original columns of the matrix A. But let's take a couple of those off so the notes don't get too busy. Well, now we have to get the null space. Whenever you're getting the null space, you're solving this homogeneous equation. We're pretty much there. We can say, let's see if we've got space. Not quite. Let's put it down here. Go. So here's our just a reminder of where we're at so far. Now to get the null space, we'll take the original matrix A. This step isn't required, but it sometimes helps a lot just for making sure we get the right output by augmenting. And it feels like the right thing to do because that's what you're doing for a null space, solving that equation. I'll say that this is, well, equal to, not quite. I don't want to redo the row reduction. It's going to be row equivalent to. We'll just borrow the work we just took and say this is 1, 0, 0, 0, 2, 0, 0, 0, -1, 1, 0, 0, and 0, 0, 1, 0. Now it's augmented with 0, 0, 0, 0, lots of zeros. Linear algebra is all about trying to get lots of zeros sometimes. And as a reminder, the variables in the system are x1, x2, x2, let me see if I can fix that. I have too many x2s. x3, x4. So this is the benefit of augmenting. Sometimes if we forget to augment, we might have thought the augment went right here, which would not have made sense for this problem. Now we can say that this implies x1 equals, we'll start solving for the free variables in terms of the basic ones. Oh, thanks for spotting that. Absolutely. That was going to be a mistake right here. Completely forgot that on this step, and I almost did on this one. Thanks for your reminder on that. We need to fix this right here. And so let's do one more row up reduction. I think we're done with this right here. We've got the matrix we needed. So it's now row reduce. And let's see, we're copying pretty much rows 3, 4, 3, and 2. So here's all those zeros. 1, 2, 3, 4, 5 of them to start. Then 0, 0, 0, 1, 0. Then 0, 0, 1, 0, 0. And finally, 1, 2. We'll take row 2, add it to row 1, and here's the fix. 0, 0, 0. Okay, now we're definitely in better position. Thanks for spotting that error right there. We've got x1, x2, x3, x4. And we just treat this as an equation. We'll have that this implies x1 equals -2, x2. x2 is a free variable. No pivots belonging here, so we'll just say it's equal to x2. And this looks weird, but it could always happen. x3 is just 0. There's nothing else there to solve for. And likewise, x4 is also 0. So that's our solution set. We want to find a basis for the null space of A. And so we could say next, AX equal to the 0 vector now implies x equals, we pull the coefficient x2, and we'll be left with -2, 1, 0, 0. So this is pretty much the null space. And if we were going to write out the null space as a spanning set, we would say null A equals the span of -2, 1, 0, 0. But we use the kind of unofficial note pencil because, again, that's not our answer. That's linearly dependent. If we want a basis, we write it out this way. The basis for the null space for that matrix A is just the constant vector, -2, 1, 0, 0. Why is it a basis? Well, it generates the entire solution set. That's the whole solution to AX equals 0. And also it's linearly independent. So we did it, folks. We have a basis for both column space and null space. Lots of row reduction to make that happen, but any questions so far? Okay, kind of a fluke that this turned out into one vector, and so we were able to just look at it and say linearly independent. But let's put down another comment. The process of solving AX equals 0 to find a null space. Now, this isn't a fluke. It always produces linearly independent vectors. So what happened in this problem will happen all the time. And this will be a really helpful concept when we're back in, say, chapter 5. In chapter 5, we're pretty much doing a lot of this to come up with an eigenbasis. That's just a basis for a specific null space. It'll be a null space of null A minus lambda I is pretty much all we're doing in chapter 5. And the lambda would be the eigenvalue. So we've been kind of trying to do this problem really since chapter 1, the moment we talked about parametric vector form, which is this right here. And we've just been building on it. We threw in a null space. Now we throw it in a basis. Well, any questions so far, folks, with the progress? Okay, so like a stack of cards, everything just builds on pretty much every single thing we did in chapter 1. In fact, studying for the final exam, it's not a bad idea to just read through chapter 1 again, because it makes a lot more sense once you have everything already laid out before us, what they were trying to say in chapter 1. So now let's carry on. We found a basis for a null space, a basis for a column space. But here's another problem we have to tackle as well. Sometimes we just have a random spanning set, not necessarily based off any matrix, so we're not talking about null space or column space, and we still want to find the basis for it. But theorem 6 is still powerful. Even if you're not given a matrix, you can just throw all this into a matrix, start row reducing, and the pivot columns will form the basis. That looks like kind of a nasty row reduction, but let's give it a try. Let's say, let A equal 1, 0, 0, 1, negative 2, 1, negative 1, 1, 6, negative 1, 2, negative 1, and 5, negative 3, 3, negative 4, and finally 0, 3, negative 1, 1. Seems like awful row reduction out of nowhere, but the reason these are such big sets of many entries, many vectors is these concepts don't seem very interesting unless you have a lot to eliminate here. So that's kind of why it's such a nasty looking row reduction. There won't be many of these on exam. I'd say 2 at the most. But let's start row reducing. Looks like we have a good start. I'll just put in 1, negative 2, 6, 5, 0. Then a lot more copying. 0, 1, negative 1, negative 3, 3, 0, negative 1, 2, 3, negative 1. And finally, here's our operation. Multiply row 1 by negative 1, add to row 4 to get 0, 3, negative 7, negative 9, and a 1. So it starts off kind of nice. Everything's all set up here. Now this time, all we need is echelon form, not row reduced because null space is not involved this time. So next step, let me see if I can just kind of fit it in there. 1, negative 2, 6, 5, 0, 0, 1, negative 1, negative 3, 3. And then not too bad for the next operations. We'll add row 2 to row 3 to get 0, 0, 1, 0, 2. Then multiply row 2 by negative 3, add to row 4 to get 0, 0. Let's see here, that's a positive 3 minus 7, so negative 4. That's going to be 9 minus 9, so 0. Negative 9 plus 1, so negative 8. Almost in echelon form, looks like we have pivots going this way. We just need to resolve what's going to happen in the next row. But if you look at that really carefully, what would we do? We would take 4 times this, add to the row below. That's all wiped out. So if you can analyze the pivot right at this stage, you're not necessarily required to complete the row reduction. We've done a lot of row reduction, so you're heavily encouraged to take shortcuts. We found the pivot columns. But we need to be very careful because these are not necessarily the right ones that form the basis. We have to go back over here and pull these. This time it was just the first 3 columns, and so we can say a basis for H is, now if you like, you could just recopy them, or you could call them V1, V2, V3 and just stick in there. It's completely up to you. Usually for the notes, just so it doesn't seem too confusing, I just write them in. 1, 0, 0, 1. Negative 2, 1, negative 1, 1. And 6, negative 1, 2, negative 1. Now, why is it a basis? It did not correspond to free variables, so this is automatically linearly independent. But even more, these columns came from here. It was already being spanned, so we have independence and spanning. And the spanning set theorem says anything that's not a pivot column is a linear combination of the others. This is essentially all we did. We just deleted the ones that did not correspond to a pivot. Now you've got a basis. Does that make sense to folks as the process? Awesome. The major danger again is don't grab these. All the purpose for this matrix is to just identify pivot columns. So that's what finding a basis looks like in this context. Any questions at the moment?
You know that the pivot columns before the reducing zero to the echelon form. Does it count for the basis?
Absolutely, yeah. So you get to this spot and find the pivot columns. The only reason it forms a basis is we already are spanning those particular columns right there. And these ones now are linearly independent, having come in from the actual pivot columns here. Does that make sense with your question there? Awesome. So this is how using the spanning set theorem works if we're dealing with Rn, so R3, R4, and so on. But a lot of these questions are actually more like this that we want to answer. In differential equations, when you go to solve a differential equation, the solution set is a basis that we were trying to come up with. Well, the solution set is going to be the span of that basis, but we want a particular set of solutions that will span and be linearly independent. So the purpose of this problem is, it's really a differential equations kind of problem. We have V is going to be the vector space of all real valued functions, so they output a real number. The domain is also real numbers. And H is going to be defined as this set for spanning three different trig functions, sine t, sine 2t, sine t, cosine t. And we need to pare it down to form a basis out of this. This is kind of tricky in a way, but one thing we can do is, let's take a look at this from just a graphical side. Not remote desktop, let's try again. So let's suppose it was just two vectors, sine t, sine 2t. If it's just two vectors, finding linear independence on these two, well, you have options. If you've heard of the Wronskian before, that's used in differential equations to find if two functions are linearly independent or linearly dependent. Or you can just graph them. You put y equals sine t, and you have a linear combination of sine t, it would look like this. Let's say it's 3 sine t. That's all we mean by linear combination. You're just rescaling it. And so graphically, it would come out like this. Y equals 3 sine t. So visually, this is what it looks like to have this be a linearly dependent set. Sine t, sine 3 sine t are dependent because the only difference between these graphs is the amplitude change. We just rescaled it. It has more vertical distance. If you put in a function that goes like this, let's say sine 2t, that breaks down majorly. This does not look like a linear combination at all. So that would tell us those two are linearly independent instead. That's not the full story. You really have to use a Wronskian. So think of example 7 as kind of a preview where all this work is trying to get to. But there's still more going on with this. There's 3 vectors, so it makes the problem even harder. Anyone see what we could do to kind of resolve the fact there's 3 vectors? Let me grab one theorem for us while we're thinking about it. What we want to use is the spanning set theorem, in particular part A, but it'd be weird if we didn't grab all of it. So let's grab it all. Okay, so with the spanning set theorem ready to go, it says, if one of the vectors is a linear combination of the remaining vectors, then the set found by removing that offending vector still will span. So this is what we would like to use. And between those 3 functions, one of them is suspicious, but that's only because I teach trigonometry after this class. I'm expecting this kind of identity on this one. It's going to be the double angle identity for that one. Exactly, good call. So we could take that function right in the middle and say, since sine 2t equals 2 sine t, cosine t, we're now using the spanning set theorem, and we can say, Well, let's decide which one to eliminate. We can either eliminate that one or that one. How about that one? That looks like the more complicated one. Let's just stick with sine 2t. We have sine t, cosine t is a linear combination of sine t and sine 2t. Should probably pause right there. What do we mean by a linear combination of sine t, sine 2t? Well, we're trying to track this definition, so that's why we wrote it. But what we're trying to express is, if you take 0 times sine t plus, let's say, 2 times, or just this one, plus sine 2t, then, let's see here, sine 2t is equal to that. So let's say equals, see here, 2 sine t cosine t. Got confused on the algebra out of nowhere. It must be late at night. But that's our linear combination that we're referring to right up here. We took 0 times the first vector, 1 times this vector, and because that wipes out, we're just really saying this all over again. But it's important to see what the definition is trying to say. That's our linear combination. Now we're going to remove a vector. The one we're removing is that one. We have h equals the span of sine t, comma, sine 2t. Well, we pared it down, but what we are trying to find is a basis. So this is the portion of the course where this is almost getting a little too far for a real exam question or a real homework question. Think of this one as an application towards what linear algebra is trying to do in differential equations. So we need to still show that this is a basis. We can argue graphically, but usually that's not a very preferred method, and it can be very confusing if there's multiple vectors. So typically what we would do next is apply the Wronskian. I'll leave it up to the class. Should we take a look at that, or should we move to the next problem, since it is an optional topic for sure? All right, let's give the Wronskian a try. It does intersect with linear algebra a tremendous amount. Linear algebra is just everywhere. And the way we work the Wronskian is we do W is our symbol. We're taking a determinant, and the first row in this determinant are the two functions or however many functions you're testing in question. So we'll put sine t, sine 2t, and here's where it gets a little bit tricky. If I had 3 functions, I would have 3 rows. The next row is the derivative, and the next row would be the second derivative. We have 2 functions, so here is the functions, and down below is the derivative of those functions. So we get cosine t, and a chain rule on this one will be 2 cosine t, or excuse me, cosine 2t. Gotcha. And thinking in these terms so far, the Wronskian seems like the right logical thing to do because we've kind of done that. We did it, well, I mean, it wasn't a Wronskian, but we've been taking determinants of stuff. And when it came out as a 0, we said A inverse does not exist. When the determinant came out non-zero, we said A inverse does exist, and we had a basis. Essentially, the Wronskian is trying to copy that process, but now it's using functions. So here's what can happen. If this equals 0 for all values of t, we have linear dependence of those functions, and that means we're kind of stuck. That would have been a basis. But if this is non-zero for one value of t in the domain, they're automatically linearly independent. We just have to show it's a non-zero function. So we go and take the determinant in the usual way, sine t times 2 cosine t. Then minus cosine t times sine tt. Almost looks like 0, but if we track the chain rule correctly, it's non-zero because of that factor of 2. These are like terms. 2 sine t cosine t minus cosine t sine t gives us sine t, cosine t, and that is not the zero function. So automatically, because we do not have the zero function, that implies, finally, we have a basis for h. This is linearly independent. Let's say that here. That implies sine t, sine 2t is linearly independent. That's not the whole question. We need independence together with spanning, which we do have, and that together gets us to our major conclusion. We have a basis. And so it forms a basis. So that's kind of a cool little trick right there. Differential equations has a lot to say about that. And if you take more and more linear algebra, you get exposed to more of these weird ideas that intersect with other math. But that's a great way to kind of duplicate with what we've been doing. Even if you have just ordinary functions, you can still use determinants to make all this happen. Well, any questions, folks, with getting through this problem here?
How did you use sine cosine t? Is that a good function?
Or from this one right here?
Put the one in the middle, the one below.
Down below? Oh, it was more of the idea of the middle step that I didn't quite take that helps out is on this first term, we have 2 sine t, cosine t, and the second term is just negative cosine t, sine t. And it's honestly really hard to read because we're just used to seeing algebra differently.
Sine 2t,
Oh, hang on. Yeah, that was a sine 2t right there. And
cosine is well.
oh, geez, I think I dropped a lot of t's on this. Let's see if we can fix this. Should have been sine t cosine 2t. So thanks for spotting that one. Let's fix that. And then finally, it should have been cosine t sine 2t. I had it there, but then I must have micro sleeped right there and dropped that term. Put it at 2t. Now that changes what I was about to say. Are these still like terms? Let's take a look. This was a cosine 2t copying down there. It's always kind of tedious when a mistake carries all the way down. So let's try again. So it was 2 sine t cosine t. And oh yeah, these are different functions. So these don't actually combine. Let's take a look. So 2 sine t cosine 2t. I think we're all set here. We said it's not the zero function, but let's see if we're really sure about that. Let's put in carefully this time. 2 sine t cosine 2t. I'm being really careful because with trigonometry, you know there's lots of identities here. It could work out to actually be 0 and we didn't know it. So let's go minus cosine t, sine 2t. We're going to plot it, and that's an interesting shape, but it's not the zero function, thank goodness. So if it's not the zero function, we're still in better shape. But thanks for spotting that. That was a weird omission on, I think it was a mistake, like here, here, and maybe here. Other questions about that so far?
I mean, so you don't need to know if it's not a zero function. Do you have to plot it into the graph or?
Well, what you'd really do with this is you'd have to use the trigonometric identities to start simplifying it. You could put cosine squared minus sine squared here and so on for this one. And just show after you simplify, it's not 0. It turns into something else. Other questions with this one so far? Okay, I think I do have one last problem on the notes. Let's see. Nothing too major, more or less a last side topic before we call it a night. It says, let B, set of vectors v1 through vn, be linearly independent set in Rn. Explain why B must be a basis for Rn. Now, this question is actually trickier than it looks now that I've reread it tonight. There's a way that this could go the other way. It might ask you explain why it is not a basis for Rn. So there's one element of this whole problem which allows it to really truly be a basis. There's the fact that there's n vectors. We're talking about a set in Rn. We mismatch there, then we automatically would not have a basis. So the idea here is a basis for Rn must, always a powerful word, this is a strict requirement. It must have n vectors. So the fact that it said Vn right here means we're in good shape. All we have to do is let A be equal to V1 through Vn. They told us it's linearly independent. And also, these are vectors in Rl, so that's a square matrix. That means the invertible matrix theorem is on the table for this one, and we can say determinant of A is not zero, and so V1 through Vn forms a basis for Rn by the invertible matrix theorem once again, IMT. Well, we did it, folks. This one's a tricky question on the very end, and pretty much all these examples on the notes here make pretty good exam questions. I can't ask them all, obviously, but this one is the only one that's kind of out of order. It's a little bit beyond what our textbook provides. However, on the third exam, let me make sure I don't forget that. On the third exam, I'll put this question as a 21th question on, as an extra credit question. I'll give you a set that looks like this. You'll calculate a Wronskian, come up with a conclusion, and determine if the functions are independent or not. That way, just for suffering through this problem with me, you ought to have some return on that. So this could be a potential exam 3 extra credit question. If it doesn't quite fit, it'll be on the final exam instead. I'll put extra credit for Wronskian. But other questions at the moment, folks, so far? Okay, we're pretty much at the end. I definitely don't want to take too much more time, but I did want to point to what we're about to do in 4.4. The goal of 4.4 is to take this, which is a tedious process, and instead, we're going to define a real isomorphism. And that isomorphism is going to go from P2 to R3. We're going to do the same kind of problem, a way harder one, showing that this is a basis by using an actual vector isomorphism. We're going to transfer everything into R3 and show how all that works. So this is where linear algebra gets pretty wild in a certain sense. To make all this happen, you have to define ideas with dimension and such. Or excuse me, you have to define the coordinate mapping. But any other questions, folks, before we call it a night officially? Okay, that's what we'll be getting into next time. Oh, sorry, question first? Okay, gotcha. Mhm.
Are they also metrics or?
The ones over here?
Yeah, polynomial.
Yeah, we're going to turn this into a matrix. Essentially, what we're going to do is, just for a fast preview, if we take this one and call it P1, we use the vector mapping here, which grabs coordinates, and we just say that the basis of P1 is going to give us, back over here, a 1, 0, 1. We just pull coefficients from the polynomial itself, and now we have something in R3. So we just do this repeatedly, pull coefficients, work in R3, and essentially just redo section 4.3 with these kinds of vectors instead. So that's the way to work smart in linear algebra. You don't want to work with this stuff. You are always just pulling coefficients. We have to know why it works, and it's through that thing right there. Awesome. Other questions or comments so far? Okay, I think this is probably a good stopping point for us then. I don't think we want to necessarily get too far in here in 6 minutes or so. So we'll be back to this section right after our weekend. Have a great night, folks, and I'll see you all next Tuesday. Yep, thanks for making it. Hopefully the rest of the class is doing well as well, but we'll just hope that they get a good YouTube video experience out of this one.